Hi, my name is Nathaniel Hanson, and I'm a member of the Robotics and Intelligent Vehicles Research Laboratory at Northeastern University. And today I'm going to be talking about my poster, which is the characterization of fundamental building blocks for cold spray additive manufacturing. The goal for this research is to create large volume cold spray forms with the assistance of robotic path planning control. The basis for this research is the triangular tessellation technique, which is well cited in the literature, but is scant in its actual documentation how to recreate. Part of our research focuses on recreating the triangular tessellation technique, documenting its parameters, and applying it toward the creation of small fundamental building blocks. At the core of our research is a MATLAB computational deposition model, which uses a bivariate Gaussian distribution to model the surface growth of a cold spray deposition. With this model, we're able to make predictions, then go out into the wild with our cold spray system, deposit simple rasters, and then compare the two. And by the tweaking of hyperparameters, we're able to yield a computational model which enables us to accurately plan and predict the forms that will be deposited by more complex sprays. Our research is driving towards what we call the fundamental building block. The goal for this is that we can take a small, repeatable, rectangular prismatic shape and use this shape as a compounding object to create larger 3D forms. And we measure our depositions that we can generate in relation to the fundamental building block by measuring the rectangularity, which is the difference between the minimal bounding box cross-sectional area and that of our deposition form. Using our deposition model, we are able to tease out a series of parameters which were likely to lead to a close approximation of the fundamental building block form. Using our 7 degree of freedom industrial robot and VRC metal spray system, we deposited copper on an aluminum substrate using nitrogen and varied the nozzle normal to the surface and the nozzle traverse speed. Our system makes use of an in situ laser profilometer, which follows the spray nozzle as it moves across the surface. It has a resolution of up to 0.1 millimeter, allowing us to measure fine perturbations in the surface of the deposition. The scanner requires 2D line scan data, which is collated into a three-dimensional model, which we can use to analyze cross sections. In our results, we have observed that through a simple number of raster paths and variations in the spray angle, we are indeed able to recreate the triangular tessellation work, as well as come up with a novel extension in towards building right triangular forms, which serve as half of our fundamental building block. And through a simple extension of this work, we are able to spray on the left-hand side of our right triangular form as shown and generate the full fundamental building block form. Future work on this project includes the creation of a process pipeline to be able to take arbitrary 3D models, slice them, and then decompose those slices into raster patterns, incorporating the knowledge that we've gained in creating triangular tessellated profiles and the fundamental building blocks. We think this approach will be successful for a large variety of three-dimensional forms. Thank you so much for your time, and I welcome any questions you have on my research.